So we're going to be looking at a situation in which we have two concentric cylinders, one of little radius little r, one of outer radius big R, of height z, and we're going to be finding out why Fanning's friction factor is always 16 over Reynolds number for laminar flow. We're going to start off with a simple force balance. We have the force of gravity acting on a liquid. So we're going to have the density of the liquid times the volume, pi r squared times z. And we're going to multiply that by g plus tau, or the shear stress, times the surface area it's acting on, so 2 pi r times z. And that's going to be equal to 0 because we have no acceleration of the liquid. You can cancel out a few terms here. We have z there, z there, pi. This becomes r to the first. So we're left with rho rg equals negative 2 tau. Rho rg equals negative 2. And then this tau becomes our viscosity times our shear stress, and the shear stress is going to be equal to dV over dr. So we're going to be left with rho rg equals negative 2 mu dV over dr. And we want to solve for velocity for right now. So we're going to have rho rg over 2 mu, negative rho rg over 2 mu, will be equal to dV over dr. And then we're going to take the integral, the indefinite integral of both sides, and then we'll solve for c in a second. But we'll take the indefinite integral of both sides. We'll have v equals negative 2, sorry, ignore the 2, negative rho rg over 2 mu. That r should not be in there because we're integrating in terms of r. So we'll have r squared over 2, so this will become a 4 plus c because it's an indefinite integral. We can solve for the c because we know that at the outer radius, the velocity of the liquid will be 0. So you can say 0 is equal to negative rho g r squared over 4 mu. And then this will become big R because we're interested at the outer radius, plus c. And then c is simply equal to negative rho times g times big R squared over 4 mu. Well, actually negative c equals negative that. So we'll just cancel out the negatives. We're left with c. We can just substitute that back in. So we have v equals negative rho r squared, r squared g over 4 mu plus rho g r squared over 4 mu. And we can substitute out this rho g over 4 mu. So we'll be left with v equals rho g over 4 mu, and then our big R squared minus our little r squared. So we have an expression for velocity, but we're interested in relating this to flow. So to start with, our volumetric flow rate is going to be equal to our velocity times our area. But we can also do this in terms of an integral of our differential areas times our velocity. So substituting and rewriting dA, we have q equals the integral from 0 to r because we want to start at the center and go all the way to the outer radius. We'll have 0 over r, or big R, or 0 to big R, I should say, times v, which is going to be equal to rho g over 4 mu big R squared minus little r squared. And then our area for each slice that we're taking, each cross-sectional area, it's just going to be 2 pi r. And then dr, we'll move part of this outside and integrate. So q equals rho g over 4 mu And actually that'll be times pi. And it's 2 pi, so the 2 and the 4 will cancel out and we'll have 2 mu. And then this little r will multiply into these parentheses. And so when we take the integral, we'll have r squared, and then that will be little r squared over 2. So we'll be left with big R to the 4th over little r, not little r, over 2 minus our little r to the 4th over 4. I went ahead and just integrated with respect to big R. We could write this out, but no need. So we'll have Q is equal to, and this term here is basically 1/2 R to the 4th. So we'll have Q equals rho G pi over 4 mu. And we'll have big R to the 4th over 2. Over 4. And then when we rewrite this, we can rewrite this in terms of d, because when we look at our expression for Reynolds number, RE is going to be equal to rho times our velocity times our diameter over mu. We have rho, we have mu, and we can pretty easily put in d for our expression, so then we'll just have to solve for v, or find a way to express v in terms of other quantities. So then we'll just have Q is equal to rho G pi, R equals D over 2, and 2 to the 4th is 16, so we'll have I think I dropped a 2 somewhere. I did, this should be 8. Sorry about that. So we have rho G pi over 128 mu, and then R to the 4th, D to the 4th. So we have rho, we have D, we have our mu, and then we need to find a way to express this with V as one of the terms. So using our old friend Bernoulli's equation, we have P1 minus P2 over, well, really P2 minus P1 over rho plus V2 minus V1 over 2 plus GZ, and actually delta Z, which for us is just going to be Z, equals our frictional heating. And oh boy, I love drawing this so much. Let me try that again. One more try. I guess that's what we're working with here. Anyways, that's going to be equal to our frictional heating, though, as we mentioned. There's no pressure drop, and the liquid is stationary, so we just have GZ is equal to our fanning friction factor. Typically, this would be negative G delta Z, but since we have a negative drop here, we can actually say this is positive. So our fanning friction factor is just going to be equal to G delta Z. And in our term for our volumetric flow rate, we actually have a term for G. So we can go and substitute our value that we can get from G here in for a G in our Bernoulli's equation, and use that in terms of our frictional heat. I might have called this our friction factor. It's not. It is our frictional heating. So then we have G is going to be equal to 128 Q times mu over rho g, no g, rho pi d to the fourth, and then times z, and that's going to be equal to our fancy f, and then from here, we can use our identity for the fanning friction factor and just plug some stuff in, and we should get our term or our result in terms of Reynolds number. And then this part of the equation stops becoming true once you add the c in there. And then we know that our frictional heating is going to be equal to 4 times our fanning friction factor. And then I believe it's delta x over our diameter. And then our v squared over 2. And then I'll just go ahead and rewrite this as such. And then we can go ahead and start canceling some of these things. Delta z. First thing I'm going to cancel is delta x and delta z, because it's just different planes of reference. But it's the same in this case. Our change in height is our change in pipe length. And then we'll have to multiply across here. Well, actually, we'll have 2 here. We're going to have to divide across by 2, so this will come out. This will become 64, I believe. We're going to have to multiply across by 1d, so this is going to become d cubed. And then we have this v squared left over. So rewriting, we have 64q mu over rho pi d cubed equals our fanning friction factor times v squared. And then from here, I've never actually solved this all the way through, so I'm kind of curious. We have this v squared. We can divide that across 2. I don't know why I didn't do that before. So we'll just have v squared here. And again, we're looking to prove that f is equal to 16 over Reynolds number. And then Reynolds number is equal to our rho v d over mu. So here we have a q, so I'm going to guess that 64, and then q is just going to be v times our delta, or our area. So we're going to have pi d squared over 4. That makes sense. And then mu. So these 2 will cancel, and this will just become 16 d squared over mu. And then we'll have rho pi, these pi's will cancel, d cubed, this will cancel, this will just become d to the first, this will cancel out. And then we have v squared, this will cancel, and then this will just become v to the first. And that'll be equal to our fanning friction factor. Let's rewrite this. We have 16 mu over rho d v, and that's actually equal to our, 16 over our Reynolds number, because 16 divided by rho v d over mu, we have, when we divide 16 by our Reynolds number, rho v d over mu, the mu will move up to the top, and then this will move down to the bottom. So there we go. There's the proof that for laminar flow, the fanning friction factor is 16 over our Reynolds number.